Now in this lecture we will find out the length of chord CB. In the drawing we have a semicircle. We know that the center of this semicircle is at this point O. Inside this semicircle we have a square DEFO, this square, and we know that the area of this square is equal to 5 units. And our mission is to find out the length of this chord CB. Okay, so first of all, because of the fact that DEFO is a square, we know that all the angles inside any square are right angles. So those 4 angles that are inside square DEFO, they are all right angles. So I'll write it down. This angle equals to 90 degrees. This angle, it is also equals to 90 degrees. This angle equals to 90 degrees. And finally, this angle, it is also equals to 90 degrees. And we know that if this is a square, we know that all the sides of any square are equal to each other. So if the length of one side is x, then the other side are also they are equal to x units in their lengths. And the area of this square equals to x times x. X times x, that is actually equals to x squared. So the area of our specific square is actually square DEFO is equal to 5 square units. Here the area, here the squared brackets is the sign for the area, so it means that the area of square DEFO, it is equal to 5 square units. So we can substitute the area by 5 because the area is equal to 5 square units. And according to this formula, the area of any square, and especially of square DEF, it is equal to x squared. So if we define one side of our square DEF as x, then the other side will be also equal to x. And therefore the area of this square DEF, it is equal to x squared according to this formula. So we found out that 5 equals to x squared. We'll take a root out of this equation and we'll get that 5x equals to the square root of 5 units. So we actually found out that one side of square DEF of a square is equal to square root of 5 units. FO equals to the square root of 5 units, EO equals to the square root of 5 units, DE equals to the square root of 5 units, and finally DF, it is also equals to the square root of 5 units. Okay. In the next step, we will join points D and O together by a straight line. By joining points D and O, we actually created the right triangle DFO. Triangle DFO, the green triangle DFO is the right triangle because of the fact that angle DFO is the right angle. So I copy the right green triangle therefore in a new page and we'll implement the Pythagoras theorem on this right green triangle. So this is the right green triangle therefore with the copy from the original drawing. We know that df equals to f4 equals to the square root of 5 units. They are both the size of the square. So we will implement the Pythagoras theorem on this right triangle therefore. So by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In this right triangle, DO is the hypotenuse, therefore the square of the hypotenuse is DO squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to DF squared plus FO squared. So DO squared, that is the square of the hypotenuse, must be equal to DF squared. DF equals to the square root of 5, therefore DF squared equals to the square root of 5 squared plus FO squared. FO equals to the square root of 5, therefore FO squared equals to the square root of 5 squared. In conclusion, we found out that DO squared equals to the square root of 5 squared, it is of course equals to 5. Square root of 5 squared is 5, so DO squared equals to 5 plus 5. That is to say, DO squared equals to 5 plus 5 is 10. Here we will take a root out of this equation and we get that DO equals to the square root of 10 units. The hypotenuse DO equals to the square root of 10 units. So here we can find out that the hypotenuse DO equals to the square root of 10 units. Here point O is the center of the semicircle. Point D is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, DO is the radius of the semicircle that is equal to the square root of 10 units. So I'm writing down DO is the radius of the semicircle that is equal to the square root of 10 units. That is to say, the radius of this semicircle equals to the square root of 10 units. What is the definition of OB? O is the center of the semicircle, B is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, OB is the radius of the semicircle that is equal to the square root of 10 units. Likewise, what is the definition of AO? O is the center of the semicircle, A is the point of the semicircle itself, therefore OA is the radius of the semicircle that is equal to the square root of 10 units. In the next step, I will present to you a new rule and we will implement the new rule in our drawing. Okay, so here, according to the new rule, that is actually rule number 1. The sum of the angles on one side of a straight line is equal to 180 degrees. So I will explain the meaning of this rule. If we have a straight line, if here AB is a straight line, we choose any point on this straight line AB. For example, this point, we define this point as point K, and here we have a side KL. AB, the straight line AB has two sides. This is the upper side and this is the lower side of AB. So if we focus on the upper side of the straight line AB at point K, here according to this rule number 1, the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of AB at point K? We have angle AKL and plus angle LKB. That is to say, the sum of the angles AKL plus angle LKB, in total the sum of those two angles must be equal to 180 degrees according to this rule number 1. The same rule is true if we focus on the lower side of the straight line AB at point K. Here the sum of this angle must be equal to 180 degrees. We actually can implement rule number 1 in our drawing. Why? Because in our drawing we have this semicircle. This is a semicircle according to what is given us in the question. And here AB is the diameter of the semicircle. In any semicircle, always here AB will be the diameter of the semicircle. AB is the diameter of the semicircle. It is absolutely a straight line. So if we focus on the upper side of AB at point O, on the upper side of AB at point O, the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of AB at point O? We have this angle and this angle that is equal to 90 degrees plus angle, the missing angle, it is angle EOB. In total, the sum of those two angles must be equal to 180 degrees according to rule number 1. So I write it down. If we focus at the upper side of the straight line AB at point O, according to rule number 1, the sum of the angles at the upper side of AB at point O must be equal to 180 degrees. So which angles we have at the upper side of AB at point O? We have this angle that is equal to 90 degrees. This is one of the angles of the square, plus the missing angle EOB. In total, the sum of those two angles must be equal to 180 degrees according to rule number 1. I'll repeat again. $90 plus angle EOB, in total they must be equal to 180 degrees according to rule number 1. Here we will subtract 90 degrees from this equation and we will get that the missing angle EOB, equals to 90 degrees, because 180 degrees minus 90 degrees, it is equal to 90 degrees. So this is a right angle. Angle EOB is a right angle. And because of the fact that angle EOB is a right angle, then the triangle EOB is a right angle. This triangle EOB is a right angle. So I'll copy the right pink triangle in a new page and we will implement the Pythagoras theorem on this right pink triangle EOB. Okay? So So this is actually the right pink triangle that I copied from the original drawing. We know that EO equals to the square root of 5 units. OB is the radius of the semicircle that is equal to the square root of 10 units. We will implement the Pythagoras theorem in order to find out the length of the hypotenuse AB of the right triangle EOB. So by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is EB, therefore the square of the hypotenuse is EB squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EO squared plus OB squared. Okay? So EB squared, that is the square of the hypotenuse, must be equal to EO squared. EO equals to the square root of 5. Therefore, EO squared equals to the square root of 5 squared plus plus OB squared. OB equals to the square root of 10. Therefore, OB squared equals to the square root of 10 squared. So in conclusion, we found out that EB squared equals to the square root of 5 squared. The square root of 5 squared is 5 plus the square root of 10 squared is 10. So in conclusion, we found out that EB squared equals to 5 plus 10, that is 15. Here we will take a root out of this equation, and we'll get that EB equals to the square root of 15. Here the hypotenuse EB equals to the square root of 15. EB equals to the square root of 15. So we found out the value of EB. Our mission is to find out the length of chord CB. So the only thing that is left to find is to find out the length of line segment CE. In order to find out the length of line segment CE, we will make a construction. First of all, we will complete this semicircle to a circle. So we completed the semicircle to a circle. In the next step, we will extend line segment EO on both sides. We will extend line segment OE towards the upper side of the circle until it touches the circle, and we will define the touching point of the extended OE and the circle as point M. In the next step, we will extend the line segment EO towards the lower side of the circle until it touches the circle, and we will define the touching point of the extended EO and the circle as point N. So here, point O is the center of the circle, point N is the point of the circle itself. This is exactly the definition of a radius. Therefore, ON is the radius of this circle that is equal to the square root of 10 units. Okay, so what is the length of EN? EN equals to EO plus ON. EO plus ON. Again, EN equals to EO plus ON. That is to say, EN equals to EO, that is equal to 5 units, plus ON is equal to 10 units. That is, so in conclusion, we found out that EN equals to the square root of 10 units plus square root of 5 units. So we can write down here that EN, the length of line segment EN, it is equal to the square root of 10 units plus square root of 5 units. Likewise, we find out the length of ME from the drawing. It is very easy to see that ME equals to MO minus EO. Again, ME equals to MO minus EO. ME equals to MO minus EO. So ME equals to MO, that is the radius of the circle, that is equal to the square root of 10 units, minus EO, that is equal to the square root of 5 units. So in conclusion, we found out that ME equals to the square root of 10 units minus square root of 5 units. We have already found out that ON equals to the square root of 10 units and EB equals to the square root of 15 units. In the next step, I will present to you a new rule and we will implement the new rule in our drawing. So it will be rule number 2. Rule number 2 is true in any circle, so I write down in any circle. In any circle. So the circle that I will draw could be any circle. If chord AB this is chord AB, intersects with chord CD, this is chord CD, chord AB intersects with chord CD, and the intersection point occurs at this point that we will define as point O. So chord AB intersects with chord CD at point O. So I write it down. If chord AB intersects with chord CD at point O, then according to this rule, that is actually rule number 2, then we get that the following equation is true, that AO times OB, AO times OB equals to CO times OD, equals to CO times OD. I repeat again on rule number 2. If chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So actually we can implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN, this is chord MN, that intersects with chord CB, this is chord CB, and the intersection point occurs at this point E. So I copy the two chords that intersect with each other in a new page, and we'll implement rule number 2 in our drawing. So the circle that I will draw, it is our specific circle, is not any circle. We will implement rule number 2 in our specific circle. This is our specific circle. We know that chord MN passes through the point, for the center of the circle, that is to say for point O. Here chord MN, this is called MN. This passes from the center of the circle, that is point O. And here we have chord CB. It intersects with chord CB at point E. This is called CB, and the two chords intersect with each other at point E. So I write it down. In our specific circle, we have chord MN that intersects with chord CB at point E. Therefore, according to rule number 2, we will get that ME times EN equals to CE times EB. Because of the fact that chord MN intersects with chord CB at point E, we'll get that according to rule number 2, ME times EN equals to CE times EB. We have already found out that ME equals to the square root of 10 minus square root of 5. We have already found out that EN equals to the square root of 10 plus square root of 5. And we have already found out that EB equals to the square root of 15. The only missing line segment is line segment CE. So here we will substitute ME by square root of 10 minus square root of 5. We will substitute EN by square root of 10 plus square root of 5. CE is the missing line segment, so we leave it as it is. Times EB. We'll substitute EB by square root of 15. We have the algebraic identity that A times B equals to B times A. Therefore, we can change the order of those two expressions, and we can write down that square root of 10 plus square root of 5 times square root of 10 minus square root of 5. This is equal to CE times square root of 15. Okay. In order to find out the value of the expression square root of 10 plus square root of 5 times square root of 10 minus square root of 5, we will use the algebraic identity that states that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to square root of 10 and b equals to square root of 5. So I write it down. A equals to the square root of 10, b equals to the square root of 5, and according to the algebraic identity that a plus b times a minus b equals to a square minus b square, our expression square root of 10 plus 5 times square root of 5 minus 5, it is equal to a square minus b square. It is equal to a square minus b square. That is to say, if a equals to the square root of 10, then a square equals to 10, of course. And if b equals to the square root of 5, it means that b square equals to the square root of 5 squared, that is 5. So it is a square minus b squared. In total, it is actually 10 minus 5. So our original expression, square root of 10 plus square root of 5 times square root of 10 minus square root of 5 equals to 10 minus 5. This is actually a square minus b square. And according to rule number 2, it is equal to CE times square root of 15. 10 minus 5 is 5, so 5 equals to CE times square root of 15. Here we will divide this equation by square root of 15, and we will get that CE equals to the square root of 15. So we actually found out that the missing line segment CE, actually here, C equals to 5 over square root of 15. We divided this equation by square root of 15. Therefore, CE equals to 5 over square root of 15. Again, I'm writing down that CE equals to 5 over square root of 15. So the missing line segment here, CE, it is equals to 5 over square root of 15. And what is the length of the line segment that we are looking for, CB? It is very easy to see from the drawing that CB equals to CE plus CB. Again, CB equals to CE plus CB. I write it down. The line segment that we are looking for is CB, and according to our drawing, we get that CB, called CB equals to CE plus EB. So CB, the code that we are looking for, equals to CE. We have already found out that CE equals to 5 over square root of 15 plus EB, EB equals to the square root of 15. So the answer to the question is that the length of this chord called CB, it is equal to 5 over square root of 15 plus square root of 15. In the next step, we will simplify this expression in order to eliminate the square root in the denominator. We will do it by multiplying square root of 15 by square root of 15, and then we will divide square root of it by square root of 15. Square root of 15 over square root of 15 is 1, so by multiplying it and dividing it by square root of 15, we actually multiplied it by 1, so we change nothing, therefore it is allowable. In this way, we created the common factor with 5 over square root of 15. So CB equals to 5 over square root of 15, and then we will multiply square root of 15 by square root of 15, and then we will divide it by square root of 15. So in conclusion, we will get that the line segment that we are looking for, that is actually CB, it is equal to 5 plus square root of 15 times square root of 15 is 15 over square root of 15. Okay, so CB equals to 5 plus 15 is 20 over square root of 15. We want to eliminate the square root in the denominator, therefore we will multiply this expression by square root of 15 and then we will divide it by square root of 15. So we know that CB equals to 20 over square root of 15. Now we will multiply this expression by square root of 15 and then we will divide it by square root of 15. We actually multiply it by 1, so we change nothing. So we'll get that CB equals to the numerator we have 20 times square root of 15 over square root of 15 times square root of 15 is 15. Here we will divide this expression, both the numerator and the denominator, by 5, and we'll get that CB, that is the line segment that we are looking for, equals to 20 over 5 is 4, so in total the numerator we have 4 times square root of 15 over 15 over 5 is 3. So in conclusion, we found out that the length of this chord CB, it is equal to either 4 times square root of 15 over 3 units, or in terms of numbers, it is equal to 5.164 units. I'll repeat again, the length of this line segment or chord CB, the chord that we are looking for, it is equal to either 4 times square root of 15 over 3, or in terms of numbers, the length of this chord called CB, it is equal to 5.164 units. In the next step, I will summarize the lecture. Okay. In the original drawing, we had a semicircle. We know that the center of this semicircle is at this point O. Inside this semicircle, we have this square DEFO, and we know that the area of this square DEFO is equal to 5 square units, and our mission is to find out the length of this chord called CB. So first of all, we know that the angles all the angles inside the square are right angles, therefore those 4 angles that is inside the square DEOF are all right angles. And we know that the area of this square is equal to 5 square units. So here, if this is a square and one side of this square is equal to x, then the area of this square, that would be any square, it is equal to x times x, that is x squared. So in our specific square, that is DEFO, we know that the area of this square is equal to 5 square units. That is to say, from one side, the area of this square is equal to 5 square units, and from the other side, the area of this square, according to this formula, it is equal to x times x, that is x squared. Therefore, in conclusion, we will find out that 5, that is the area of this square DEFO, it is equal to x squared. That is the area of the square according to this formula. So 5 equals to x squared. Here we took a root out of this equation, and we found out that x equals to the square root of 5 units. So here, one side of this square is equal to square root of 5 units. Okay, then we join points D and O together by a straight line. In this way, we created the green right triangle, triangle DOF. So I copied triangle DOF in a new page and we implemented the Pythagoras theorem on this green right triangle DOF. This is the right green triangle DOF that I copied from the original drawing. We know that DF equals to the square root of 5 units, FO equals to the square root of 5 units, and this angle equals to 90 degrees because it is 1 out of 4 angles of the square. And here we can implement the Pythagoras theorem in order to find out the value of the hypotenuse DO in the right triangle DOF. By PT, the equation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle is DO, therefore the square of the hypotenuse is DO squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to df square plus FO square. So in conclusion, we found out that DO square equals to df square plus FO square. So DO square, that is the square of the hypotenuse, equals to df square. df equals to the square root of 5, therefore df square equals to the square root of 5 square, plus FO square. FO equals to the square root of 5, therefore FO square equals to the square root of 5 square. So in conclusion, we found out that DO square equals to square root of 5 squared, that is 5, plus square root of 5 squared, that is 5. That is to say, DO square equals to 5 plus 5, that is 10. Here we took a root out of this equation and found out that DO, the length of the hypotenuse, DO, it is equal to the square root of 10 units. Here we can write down that DO, the length of the hypotenuse DO, it is equal to the square root of 10 units. Here O is the center of the semicircle, D is the point on the semicircle itself, therefore DO is the radius of the semicircle. That is to say, here DO is the radius of the semicircle, that is equal to the square root of 10 units. Okay? Here point O is the center of the semicircle, point B is the point on the semicircle itself, therefore OB is the radius of the semicircle, that is equal to the square root of 10 units. Likewise, if you relate to line segment AO, point O is the center of the semicircle. Point A is the point on the semicircle itself, therefore AO is the radius of the semicircle, that is equal to square root of 10 units. Then I presented to you rule number 1 and we implemented rule number 1 in our drawing. According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. So if AB is the straight line, we will choose any point on the straight line AB. For example, we choose this point that we define as point K. Here we have side KL, and if we focus on the upper side of the straight line AB, that is to say on this side, at point K, here the sum of the angles according to this rule, rule number 1, must be equal to 180 degrees. So which angles we have at the upper side of AB at point K? We have this angle, that is angle AKL, plus this angle, that is angle LKB. In total, the sum of those two angles must be equal to 180 degrees. That is to say, angle AKL plus angle LKB, in total, they must be equal to 180 degrees according to this rule, rule number 1. The same thing is true about the lower side of AB. So if we focus on the lower side of AB at point K, here the sum of those, the side of this angle must be also equal to 180 degrees. We can implement rule number 1 in our drawing. Why? Because in our drawing, we know that according to what is given us in the question, this is a semicircle. In any semicircle, always this part is the diameter of the semicircle. That is to say, AB is the diameter of the semicircle. AB is the diameter of the semicircle. It is absolutely a straight line. So, because of the fact that AB is a straight line, you can implement here rule number 1. So if you focus on the upper side of the straight line AB at point O, here the sum of the angles must be equal to 180 degrees according to rule number 1. Okay? So, which angles we have at the upper side of AB at point O? We have this angle that is equal to 90 degrees, plus this angle that is actually angle EOB, the missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule number 1. I'll repeat again. and the upper side of AB is point O. According to rule number 1, the sum of the angles must be equal to 180 degrees. Which angles we have at the upper side of AO at point O? We have one angle that is a right angle, and the other angle that is the missing angle EOB. In total, the sum of those two angles must be equal to 180 degrees according to rule number 1. We subtracted 90 degrees from this equation, and we found out that the missing angle EOB equals to 180 degrees minus 90 degrees, it is 90 degrees. So we found out that the missing angle here, this angle EOB equals to 90 degrees. And because of the fact that the angle EOB equals to 90 degrees, it means that triangle, the pink triangle EOB is a right triangle. Therefore, we can implement the Pythagoras theorem on the right pink triangle EOB. So I copied the right pink triangle EOB in a new page and we implemented the Pythagoras theorem on it. This is the right triangle EOB that I copied from the original drawing, the right pink triangle. We know that EO equals to the square root of 5 units, OB equals to the square root of 10 units, and EB is the missing, side, that is actually the hypotenuse of this right triangle. Now we'll implement the Pythagoras theorem in this right triangle in order to find out the hypotenuse, the length of the hypotenuse EB. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is EB, therefore the square of the hypotenuse is EB squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EO squared plus OB squared. Okay, so actually EB squared equals to EO equals to the square root of 5, therefore EO squared equals to the square root of 5 squared, plus OB squared. OB equals to the square root of 10 units, therefore OB squared equals to the square root of 10 squared. So in conclusion, we found out that EB squared equals to the square root of 5 squared plus square root of 10 squared. That is to say, EB squared equals to the square root of 5 squared. The square root of 5 squared is 5, plus the square root of 10 squared is 10. So in conclusion, we found out that EB squared equals to 5 plus 10. 5 plus 10 is 15. So EB squared equals to 15. We took a root out of this equation, and we found out that EB equals to the square root of 15 units. So here EB, the hypotenuse EB equals to the square root of 15 units, and again here EB, line segment EB equals to the square root of 15 units. So we actually found out our mission is to find out the length of chord CB. We already found out that EB equals to the square root of 15 units. The only thing that is left to find in order to find out the length of chord CB is to find out the length of line segment CE. In order to find out the length of line segment CE, we did the construction. We actually completed this semicircle to a circle, and then we extended line segment OE on both sides. We extended line segment OE on the upper side by a straight line until it touches the circle at point M, and then we extended line segment EO towards the lower side until it touches the lower side of the circle at point N. Here, what is ON? Point O is the center of the circle, point N is the point of the circle itself, therefore ON is the radius of the circle that is equal to square root of 10 units. Okay, and what is the length of EN? From the drawing it is very easy to see that EN equals to EO plus ON. EN equals to EO plus ON. That is to say, EN equals to EO, that is square root of 5 units, plus ON, that is square root of 10 units. In conclusion, we found out that EN equals to square root of 10 units plus square root of 5 units. Likewise, what is the length of line segment ME? The length of line segment ME, it is equal to MO minus OE. ME equals to MO minus OE or EO. So ME equals to MO, that is the radius of the circle, that is equal to square root of 10 units, minus EO, that is equal to the square root of 5 units. In conclusion, we found out that ME equals to the square root of 10 minus square root of 5. Then I presented to you a new rule, and we implemented the new rule in our drawing. According to the new rule, that is actually rule number 2, that is true in any circle. In any circle, the circle that I drew would be any circle. In any circle, if chord AB intersects with chord CD at point O is the intersection point between the two chords, then according to this rule, rule number 2, the following equation is true that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. AO times OB equals to CO times OD. You can implement rule number 2 in our drawing. Why? Because in our drawing, we have chord MN. This is chord MN that intersects with chord CB. This is chord CB. In the intersection point between the two chords occurs at point E. Therefore, we can implement here rule number 2. So I copied the two chords that intersect with each other in the new page and implemented the rule number 2 in our drawing. Here, this is chord MN that passes through the center of the circle that intersects with chord CB is point E. Point E is the intersection point between the two chords. Therefore, according to rule number 2, we will get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. We have already found out that ME equals to the square root of 10 minus square root of 5. EN equals to the square root of 10 plus square root of 5. And EB equals to the square root of 15. So we substituted ME by square root of 10 minus square root of 5. We substituted EN by square root of 10 plus square root of 5. CE is the missing line segment, so we will leave it as it is. We left it as it is, and EB equals to the square root of 15, so we substituted EB by square root of 15. And we found out that square root of 10 minus square root of 5 times square root of 10 plus square root of 5 equals to CE times square root of 15. According to the algebraic identity that A times B equals to B times A, we can substitute the two expressions with each other. We can substitute the orders of the two expressions with each other. That is to say, we can write down square root of 15 plus square root of 5 times square root of 10 plus square root of 5 times square root of 10 minus square root of 5. So we substituted the two expressions with each other in the order, and according to rule number 2, it is equal to CE times square root of 15. In order to find out the value of this expression, we use the algebraic identity that states that A plus B times A minus B equals to A squared minus B squared. Okay, in our specific expression, we know that A equals to the square root of 10 and B equals to the square root of 5. I repeat again, in our specific expression, A equals to the square root of 10 and B equals to the square root of 5. And this expression equals to A squared minus B squared. According to this algebraic identity, that A plus B times A minus B equals to A squared minus B squared. So, the expression equals to A squared minus B squared. If A equals to square root of 10, it means that A squared equals to 10, and if B equals to square root of 5, it means that B squared equals to 5. So A squared minus B squared will be equal to 10 minus 5. And A squared minus B squared, and this expression, actually, this expression according to rule number 2 equals to CE times square root of 15. Therefore, 10 minus 5 equals to CE times square root of 15. 10 minus 5 is 5, and 5 equals to CE times square root of 15. Here we divided this equation by square root of 15, and we found out that CE equals to 5 over square root of 15. Okay? Here we found out that the missing line segment CE equals to 5 over square root of 15. We are looking for the length of chord CB. What is the length of chord CB? From the drawing, it is very easy to see that the length of chord CB equals to CE plus CB. Again, CE plus CB equals to CE plus CB equals to CB. Okay? Here, CB equals to CE plus CB. We have already found out that C equals to 5 over square root of 15 and EB equals to the square root of 15. So the answer to the question is that this chord CB equals to 5 over square root of 15 plus square root of 15. In the next step, we actually just simplified this expression because we want to eliminate the square root in the denominator. In order to eliminate the square root, we actually multiply square root of 15 by square root of 15, and then we divide it by square root of 15. In this way, we actually found the common factor with this expression, that is square root of 15. Square root of 15 over square root of 15 is 1, so when you multiply someone by 1, it will change nothing. Therefore, it is allowable to do it. So here, CB equals to 5 over square root of 15, and then we took square root of 15 and we multiplied by square root of 15, and we divided by square root of 15, so we change nothing. And in conclusion, we found out that CB equals to 5, and plus square root of 15 times square root of 15 is 15. So in conclusion, in the numerator, we have 5 plus 15, and in the denominator, we have square root of 15. Okay, so CB equals to 5 plus 15, that is 20, over square root of 15. So we found out that CB equals to 20 over square root of 15. Here we multiply this expression by square root of 15, and then we divide it by square root of 15 in order to eliminate the square root in the denominator. So the expression is 20 over square root of 15. We multiply it by square root of 15, and then we divide it by square root of 15. We actually multiply it by 1, so we change nothing. Therefore, it is allowable. So CB equals to 20 times square root of 15. This is what we have in the numerator. In the denominator, we have square root of 15 times square root of 15 is 15. This way, as you can see, we eliminated the square root. We left only 15 without the square root. Okay, so in conclusion, we found out that CB equals to 20 over square root of 15 over 15. Here we divided both the numerator and the denominator of this expression by 5. So here 20 over 5 is 4. So in total, in the numerator, we have 4 times square root of 15. In the denominator, we have 15. 15 over 5 is 3. So in conclusion, we found out that the length of this line segment CB, or the length of this chord CB, it is equal to either 4 times square root of 15 over 3 square units, or in terms of numbers, the length of this chord CB equals to 5.164 units. Okay, thank you very much.